So this is a subject which is a little bit different from what has been done in the conference, but let me just explain what the intention is. I will explain in general the deformation of the classical Hodge theory, of the classical Laplacians that we're accustomed to use. And this deformation is not an obvious one. That is, it's not the one that you would just see, obviously, as a deformation. In particular, the operators which will emerge in this deformation of Laplacians will not be self-adjoint. They will not be elliptic. They will be sort of hypoelliptic, which means in a certain sense it's more difficult than ellipticity, but in some sense it's subtler. And these operators, this deformation, is intimately related to the underlying geometry of the given manifold, in particular to the geodesic flow. The reason for doing this are many. There is not only one reason for doing that. There are actually now application of this deformation in various fields of mathematics, in real geometry, in complex geometry, in the trace formula. But in some sense, every time, the reason for doing this is that by moving in the hypoelliptic world, which actually consists in enlarging the original space on which you work, you have more space. You can move more easily. Strangely enough, things in some sense, by moving with high degrees of freedom, allows you to do things which are completely forbidden in our world. So in particular, let me just give an application in complex geometry that we will see later on. When we studied non-Kähler manifolds, in which you cannot find a Kähler form, this is an obstruction to proving certain kind of results. And we will see that, or maybe we will guess, that by moving to this hypoelliptic deformation, these obstructions which exist in our common mathematical world can be, in some sense, properly lifted. So that's one motivation, moving away from the classical world, trying to give more space and hoping to solve new problems. Now, the applications have been given in 3 different fields. It doesn't mean that it's always the same machine. The machine is adapted to the geometry that you're considering. And I will illustrate this in 2 contexts. One which is relatively simple, which is de Rham theory, Hodge theory for the de Rham complex, and also in the context of Dolbeau theory. So first of all, elliptic operators. So you give yourself X to be a Riemannian manifold, and you consider the Laplacian, the Laplace-Beltrami operator delta X. So it's well known that minus delta X is an elliptic operator. Its principal symbol is psi square. It's a function on the cotangent bundle, and it's elliptic because this symbol is invertible for psi non-zero. So hypoellipticity is a weaker property. These hypoelliptic operators in general are not elliptic. So hypoellipticity means, for all practical purposes, that in spite of the fact that they are non-elliptic, they do share some of the properties of elliptic regularity. Okay, I will not say much about what hypoellipticity is, but in some sense, from the analytic point of view, they are almost as good. So the first example, in some sense, which appeared in the literature is an operator introduced by Kolmogorov in 1934. That's an operator in 2 variables, x and y, which is obviously not elliptic because it doesn't have a second differentiation in the variable x. And actually, when you look at this operator in 2 variables, you find that there is a vector field y d over dx. And this y d over dx, it's a generator of the geodesic flow. So certainly Kolmogorov was not seeing it this way, but we will recognize it this way. So this operator, in some sense, is already the shadow of the hypoelliptic Laplacian already appears in the literature in Kolmogorov. And actually, the operator of Kolmogorov is a model of hypoelliptic operators studied by Hermonda. So it verifies the assumptions in a celebrated paper. So what is the hypoelliptic deformation? So you give yourself again X to be a Riemannian manifold. And I consider the Laplace-Beltrami operator, delta X, and also Z to be the generator of the geodesic flow. So the generator of the geodesic flow, it's a vector field on the total space of the tangent bundle. Okay, so it's a vector field, but on a bigger space, not on the original space. So what is this idea of hypoelliptic deformation? So I wrote here a diagram. On the left-hand side of the scale version of Laplacian for b equals 0. On the right-hand side, you have the generator of geodesic flow viewed as an operator, differential operator of order 1. And so the idea is that there is a family of hypoelliptic operators, LB, indexed by B, acting on the bigger space, X script, which again is the total space of the tangent bundle, exactly like the geodesic flow, that interpolates properly between the Laplacian for b equals 0 and the vector field for b equals infinity. So already you see that there is something fishy here because these two operators on the left and right-hand side do not act on the same space. One is acting on the base space, the other is acting on the bigger space. So the idea of the interpolation, in some sense, looks like interpolating between a giraffe and an elephant. Right. And so we will try to make sense of what the interpolation means and also how to construct it naturally. What I mean by giving geometric arguments which will make this interpolation natural. So first of all, what we mean by Laplacian. Actually, by Laplacian, we do not mean only the Laplace-Beltrami operator. This will just be a tiny case. By Laplacian, we mean any geometrically defined Laplacian, like the Hodge Laplacians in real and complex geometry, or the square of the Dirac operator, or the Casimir operators. So I will explain this in few special cases again. Every time the deformation will be specific to the geometry that we look at, but in some sense there is a common feature, and I will just sort of explain this common feature first. So each deformation is done in its category for a purpose specific to that category. So in most cases, the deformation actually, to understand it, is not directly done on the Laplacian itself. It's done on the first order operator, the Laplacian squares. So in other words, the Hodge Laplacian is a square of a first order elliptic differential operator, which is a Dirac-like operator. You also have Dirac-like operators in complex geometry. So actually, to understand the deformation, it will be done at the level of these first order differential operators. So what is the hypoelliptic Laplacian used for? First of all, the deformation preserves subtle spectral invariance, in spite of the fact that we move from a category of operators which are elliptic to hypoelliptic, which seem to have fundamentally different spectral theory. There are subtle spectral invariants which are preserved. Certain questions which are insolvable in the elliptic world with elliptic operators become easier with hypoelliptic operators. So this goes to the general philosophy of people working with hypoelliptic operators. They always claim that it's harder to do that, and we will see that from a geometric point of view, to a certain extent, it's easier to work with those ones. On locally symmetric spaces, the deformation will be essentially isospectral. In the present talk, we will consider, as I mentioned, the case of Durham and Dolbeau Laplacians. So let me show you, first of all, how this hypoelliptic Laplacian looks like. How does it look like? So I consider the manifold X script, which is a total space of the tangent bundle, with coordinates X, which is in the base manifold, and Y, which is in the fiber. So in other words, this X script has double the dimension of the original manifold. So the first operator I will consider is the harmonic oscillator along the fiber. So Riemannian manifold, you have the vector fibers are Euclidean vector spaces. They are equipped with an operator which was well known in quantum mechanics, that the harmonic oscillator, which I wrote in this way. So the Laplacian is a fiber-wise Laplacian. Y square is just a normal square of the coordinate. N is a dimension. That the harmonic oscillator, it's a scalar self-adjoint operator whose spectrum is actually the integers. That's a fundamental operator in quantum mechanics. So this is the first component of the hypoelliptic Laplacian. The second component will be the generator of the geodesic flow. This is a vector field in the XY variables. So actually, I wrote it in geodesic coordinates at the given point X. Essentially, Z is a sum of yi, y are the coordinates in the tangent bundle, times d over dxi. So in other words, on this big space, the base is x, the fiber is tx, you have a vector field which is essentially like this. It's a horizontal vector field in some sense. Sum of y d over dxi. And so the general form of any hypoelliptic Laplacian is a combination of these two. So you have the harmonic oscillator, which just differentiates along the fiber with a factor 1 over b squared, and the second term is the geodesic flow with a factor 1 over b. And there are other terms which are related to the underlying geometry that you consider. So if you look at this operator, you see immediately it's not elliptic because it just differentiates twice in the fiber direction. It is not self-adjoint because there is a vector field, and this vector field tends to be skew-adjoint, but it is hypoelliptic in the sense of Ormonder. And what you see is that this operator actually, in some sense, it's a known operator in sort of statistical physics. Actually, it's a geometric form of the Fokker-Planck operator. So, as I mentioned, this operator is hypoelliptic by Ormonder. And so, what you see is that if you make b tend to 0 in this operator does not converge, obviously. Actually, it blows up. So when b tends to 0, it blows up, and so it's counterintuitive that actually the result of the theory will be that this operator deforms the original operator on the base by a mechanism that I will try to outline later on. So when b tends to infinity, this is easier. By rescaling coordinates, it's easy to see that LB converges to the generator of geodesic flow just by doing a rescaling of coordinates. So b tend to infinity, in some sense, geometrically, is easy to see that. B tend to 0 is a subtle thing, the fact that the operator deforms a Laplacian. So let me try to explain how can we obtain geometrically an operator like that from first principles. So first of all, classical Hodge theory on the manifold X, on the original manifold. So you give yourself a Riemannian manifold, we consider the de Rham complex, and so this complex is equipped with the L2 scalar product. You construct the Laplacian as the anti-commutator of dx and dx star being the L2 adjoint of dx. So this is the Hodge Laplacian. Actually, if in the L2 product, you modify the L2 product, and what actually you modify it by changing the volume form, simply by scaling the volume form by the e to the minus 2tf, where f is a function, then you get a new Hodge theory that's actually the Hodge-Witten Laplacian. And this deformation was considered by Witten as a method to interpolate between classical Hodge theory for t equals 0, and when t tends to infinity, actually what you can show is that the theory in the proper sense localizes on the critical points of the function. So actually Witten used that to give an interpolation between Hodge theory and Morse theory. So in some sense, the parameter b will play a sort of role of analog to the parameter t. So as a sort of preliminary to the construction of the hypoelliptic Laplacian as a Laplacian, we'll consider something that I'll call the symplectic Laplacian. So you give yourself m omega to be a symplectic manifold. And so what I'm saying is that in the same way as when you have a metric, you can define a scalar product between smooth forms using the metric. You can use a symplectic form. The symplectic form also makes that on the cotangent bundle, you have inherited non-degenerate pairing. And this non-degenerate pairing gives you also a non-degenerate pairing between smooth forms. Exactly where you simply replace the metric by the symplectic form. So let me call dm dash the formal adjoint of dm with respect to the symplectic pairing. So what you find is that if you compute the Laplacian, the anti-commutator of the de Rham operator with this dash adjoint, with the symplectic adjoint, what you find is that you get 0. This is a very easy statement. So 0, of course, is not a hypoelliptic operator. This is for sure. So what this means is that we've gone too far. In our enthusiasm to build something, an exotic theory, we've gone too far. We got the 0 operator. So let's try to get something non-trivial now. So the symplectic Witten Laplacian. I mentioned before that to construct the Witten Laplacian, what Witten did was modifying the L2 scalar product by modifying the volume. We're going to do exactly the same thing. In the symplectic pairing, we are going to correct the symplectic form or symplectic pairing by the exponential of a function. So in other words, you give yourself a function, h script, which is a smooth function, m into r, and now you take the symplectic adjoint, but with respect to this extra, by taking into account this extra volume form. And so, what you find is the following. When you have a function h, you have the corresponding Hamiltonian vector field, xh, canonically associated with h. This is part of the general mechanism of, let's say, classical mechanics. So let me call zh to be the Hamiltonian vector field associated with h. And then what you find is that the symplectic Laplacian now, the symplectic written Laplacian, is given by a first-order differential form. Not second order, but first order. That the Lie derivative operator in the direction of the Hamiltonian vector field. So we see already that the first order operator can be a Laplacian in the proper sense. So let me now reformulate the interpolation property that I claim to be true for the hypoelliptic Laplacian. I give myself again X, a Riemannian compact, and X script, this total space of Tx, which is the same as T star X by the metric. So, as we know, X script is a symplectic manifold. The cotangent bundle is a symplectic manifold, and I will introduce as a Hamiltonian half of y squared. This is a function which generates the geodesic flow in the sense that the geodesic flow is just the Hamiltonian vector field corresponding to the Hamiltonian H. So that the interpolation now between the Hodge Laplacian and let me say the Lie derivative for the geodesic flow. One is an operator of order 2 on the base. The Lie derivative is an operator of order 1 on the total space. So this interpolation, which looks strange, becomes an interpolation between a Riemannian Laplacian and a symplectic written Laplacian. Okay, so in other words, it becomes an interpolation between two objects which algebraically lie in the same category. And so, what we shall do to obtain the sort of intermediate constructions is exactly first to try to interpolate between the metric GTX and the symplectic form. So how can we do that? It's very simple. So I will construct eta B, which is a bilinear form now on the tangent bundle to the space X script. Okay, I had originally the metric, which was a bilinear form on the base. I had the symplectic form, which is a bilinear form on the total space of the cotangent bundle, and I will build another bilinear form on the tangent bundle. And how shall we do that? We will simply interpolate between the scalar product and the symplectic form. So how do we do that? We take two vectors, u and v, which are tangent to the total space. We project them down on the base. We take the metric product with respect to the metric GTX, and we add to it the symplectic form. And eventually, we add a multiple of the symplectic form. What you find is that this pairing is neither symmetric nor antisymmetric, but it is non-degenerate. That's extremely easy to see. It's non-degenerate for B positive. For B positive, it is non-degenerate. So since it's non-degenerate, again, we can use it to define a non-degenerate pairing between smooth forms, simply by duality. Exactly the way we did in the symplectic case, or the way that you do when you have a metric, right? You use this eta B as a method to construct a non-degenerate pairing between forms. And so, what you find is that eta B, in the proper sense, for B equals 0, it's just a metric on the base, which is completely degenerate, actually, as a pairing on the total space. But for B equals infinity, what is the leading term is a symplectic form. And so we hope from that if we construct the Hodge theory associated with this interpolating family eta B, we'll get a family of interpolating Laplacians. So this is exactly what we shall do. So again, H is half of y squared, that the Hamiltonian for the geodesic flow is equals ZH. I introduce the bilinear pairing between smooth forms starting from the form eta b, it gives a pairing between the smooth forms. I have a volume form, which is actually the symplectic volume form, so there is no problem here. And I construct the adjoint of the operator dx with respect to this bilinear pairing. Okay? I have a non-degenerate bilinear pairing, I have the map dx, and I construct its adjoint dxb star. And then I form the corresponding sort of Hodge Laplacian in which the classical adjoint is replaced by a bizarre adjoint with respect to a new bilinear pairing. So let me give you the formula for this sort of fake Laplacian. So here's the formula. Yes? Yes? Sorry, excuse me.
It's an integral over the total space?
Total space, right. It's a pairing on the total space now. We're working on the total space. So we're pairing between smooth forms on total space. So what we have done actually is create a bizarre bilinear form, which is non-symmetric. Actually, it can be symmetrized. I won't talk about this, but it doesn't matter. Okay, so we get a new Laplacian. And this Laplacian, if you look at it, I mean, you have to look at it well. You see a first term, which is scaled with 1 over b squared, which is a fiber-wise harmonic oscillator, as I mentioned before. In the end, you have the generator of the geodesic flow, more precisely the Lie derivative associated with the geodesic flow, and in between the operators of order 0, which are geometric operators that I will not comment. In particular, you see appearing the curvature of the Levi-Civita connection. So if you look at this operator, it has the form of a hypoelliptic Laplacian, harmonic oscillator plus generator of geodesic flow, and it has been obtained as a Laplacian. Okay, so it has been obtained as a bizarre Laplacian by modifying the type of the bilinear form. So when acting on smooth functions, this is actually the scalar hypoelliptic Laplacian that I described at the beginning. So the operator I gave at the beginning, in some sense, is a fake Laplace-Beltrami operator. So let me now try to explain why does this operator, when b tends to 0, in some sense converge to the original Laplacian. Okay, so what we shall show actually is give a sort of formal argument showing not that the operator converges because it explodes, but what we'll find is that in the proper sense, the resolvent of this operator will converge as b tends to 0 to the resolvent of the operator on the base in the proper sense. So let me just consider this operator acting on functions, so that the weighted combination of the harmonic oscillator and geodesic flow. So, as I mentioned, H is self-adjoint, positive, and let me just mention this, that the kernel of H, the kernel of the harmonic oscillator, its span is one-dimensional and is spanned by the Gaussian function. So you have this fiber-wise, you have this family of Gaussian functions in the fiber. And so, what you find when you look at this operator here is that Z is actually odd in the variable y. Obviously odd, it's linear, and so it maps the kernel of H, the harmonic oscillator, the Gaussian, into its orthogonal. Okay, if you multiply a Gaussian by a linear function, you go into the L2 orthogonal to the kernel of H. This is extremely easy to see, and so let me write the matrix structure of this operator LBX. I write its matrix structure with respect to the natural splitting of the L2 space between the kernel of H and its orthogonal. Right? You have the H, the kernel of H is the functions which are Gaussian along the fiber, and you just write the operator LB as a matrix, a 2x2 matrix. And what you find is that as b tends to 0, the matrix actually has a preferred 2x2 structure in which actually on the orthogonal to the kernel you just have h over b squared, and the fact there is 0 here on the upper left corner just reflects the fact that Z maps the kernel of H into its orthogonal. Okay, so let's look at this as a finite dimensional matrix. And let's try to compute the corresponding resolvent and find the asymptotic of the resolvent of this matrix. So now we treat this as a finite dimensional matrix. Let's do that. So when you have a 2 by 2 matrix, 2 by 2 where the pieces are matrix, you can invert the matrix. That's by Gauss method. And what you find is that if you take the behavior of the resolvent is simply lambda minus LBX minus 1, that you just add a constant and you invert. What you find is that the resolvent, when B tends to 0, actually concentrates on the kernel of H. This is just finite dimensional algebra. It concentrates on the kernel of H, and actually the leading term that you obtain as B tends to 0 is itself a resolvent. And that the resolvent, something which is highly nonlinear in the coefficients. It's a resolvent of P is the orthogonal projector on the kernel, Z, H minus 1, Z, P minus 1. Okay, so in other words, this resolvent collapses to the resolvent of an operator acting on a smaller space, which is the kernel of H. If you just do this formally in our infinite dimensional case, what you find, first of all, is a kernel of H. These are functions which are Gaussian along the fiber. This is the same as functions on the base. So kernel of H actually are just functions on the base. And if you compute in this infinite dimensional case, P, Z, H minus 1, Z, P, what you get is half the Laplacian. Okay. So that explains, in some sense, by sort of formal arguments, why the limit of the resolvent of the hypoelliptic operator converges as B tends to 0 to an operator which collapses on the smooth function of the base manifold, and it is the resolvent of the Laplacian. It also explains why, starting from an operator which differentiates 1 in the base direction, which is a geodesic floor, you get something which differentiates twice. You see P, Z, H minus 1, Z. 1 plus 1 is equal to 2. Right? That's, in some sense, that's the explanation. If you look at Z, H minus 1, Z, P, anybody familiar with spectral sequences recognizes something that you often meet when diagram chasing with spectral sequences. This is not an accident, but I will forget about that. So let me briefly explain applications of this theory, first of all, in the context of Durham theory. Let me just remind you very briefly on the Chigger-Muller theorem. So analytic torsion is a spectral invariant of the classical Hodge-Laplacian. It's actually obtained via the determinant of the Laplacians in various degrees. You can obtain the determinant from the zeta function by looking at the derivative at 0 of the zeta function. That's a formal version of the log of the determinant. So this analytic torsion was used by Reisinger to define the Reisinger metric on the determinant of the cohomology. So actually, I had to introduce before the coefficient bundle. Everything that I said mentioned with real coefficients can be also extended to the case we have a flat coefficient bundle. And so using analytic torsion, you can define a metric on the determinant of the cohomology, which is a sort of real analog of the Quillen matrix in complex geometry. So the Chigger-Muller theorem asserts that this metric that you use, that you construct using the determinant of the Laplacian, coincides with the Reiner metric, which is computed combinatorially. Okay, this is the content of the Reisinger conjecture proved by Chigger and Muller. So the proof I gave with Dong uses the Witten deformation. So elliptic and hypoelliptic torsion. So this is a result that I proved with Lebeau, is that actually the elliptic Reisinger metric that you construct using the determinant of the Laplacian, in the elliptic case, is preserved by the hypoelliptic deformation. So this result is not easy, but there is a history behind it. There is something called the Fried conjecture, which relates the Riemann metric to something which it can compute using the zeta function associated with the closed geodesics. In some sense, this result by myself or Lebeau should be viewed as a first step to proving this conjecture in general. Now, let me move to complex geometry, Dolbeault complex and Hodge theory. If you give yourself X to be a compact complex manifold and E nabla E second to be a holomorphic vector bundle, then you can introduce the Dolbeault complex, where you replace the construction I gave before, the D operator, by the D bar operator. So let me give myself Hermitian metrics, GTX and GE, to be a Hermitian metrics on the tangent bundle and on E. Then you can construct the Hodge Laplacian, which is, again, an elliptic second-order differential operator. So, what I shall do is the following. I will give another motivation to the construction of the hypoelliptic deformation, but this time in the context of complex geometry. What I will show, first of all, is that Schoenweill theory is a Hodge theory. It's a fake Hodge theory in which actually it's as fake as the Hodge theory I considered before in the context of the Ram complex. So I will show to you how to view classical Schoenweill theory as a Hodge theory. So first of all, I introduce tilde, which is an automorphism of T star XX, which maps F, one form, into minus F. And so, actually, this automorphism can be mapped to an anti-automorphism of the exterior algebra. In other words, you take a form and you make it an anti-automorphism, you interchange the order, and you replace each component by minus its component. So actually, it's just a way of associating to a P form another form with a 1 minus 1 to the P plus 1 over 2. This doesn't matter. So if I give myself two smooth forms on X, I introduce the following pairing between the forms, which is essentially the intersection pairing. In other words, I take the form alpha, I introduce some sign, I get a form alpha tilde, and I wedge it with beta bar. This is actually a non-degenerate pairing, and actually it's a Hermitian form. It is not positive, but it is Hermitian, which means that it's non-degenerate, and when you interchange alpha and beta, you get the conjugate. So actually, this Hermitian form is of signature infinite, infinite. So if I try to compute the adjoint of the de Rham operator with respect to this Hermitian form, what you find is that the de Rham operator is self-adjoint. What you find is that the adjoint of the D bar operator is just the D operator. The adjoint of the D operator is a D bar operator. And what you find ultimately, let's say, is that the Dolbeault, let's say the Dolbeault Laplacian, D bar anti-commuted with its adjoint is D bar anti-commuted with D, which is 0. Again, we have gone too far in the hypoelliptic direction. But let's proceed in this line, along this line. If I give myself E to be a holomorphic Hermitian vector bundle, then by extending this pairing between forms to pairing between forms twisted by sections of the vector bundle, what you find is that nabla E second, its adjoint with respect to this new bilinear pairing is just given by nabla E prime. That the Chern connection, okay? You have the Chern connection is made of two components, nabla E second, nabla E prime, which depends on the metric. So that actually the curvature of the vector bundle, which is the anti-commutator of nabla E second and nabla E prime, can be viewed now as a sort of generalized Hodge Laplacian. It's the anti-commutator of nabla E second with its adjoint, and actually this operator is nilpotent. Okay, is nilpotent because of the form piece. If you take the curvature and multiply it many times by itself, you get 0. So in some sense, Chern-Weil theory is a sort of bizarre Hodge theory in which the Laplacian becomes nilpotent. So the question will be, can we interpolate between classical Hodge theory for the Dolbeault complex and Chern-Weil theory by viewing these two theories as Hodge theories? So we know the original theory was a Hodge theory, but now we understand that Chern-Weil theory is also a Hodge theory. Can we interpolate between it in the proper sense? So let me just explain something very simple again. You give yourself a Hermitian manifold, that is, you introduce, let's say, omega x, which is a fundamental 1-1 form, not closed or anything. And what you find is that the multiplication by I omega x, multiplication in the exterior algebra, is a self-adjoint. It's a self-adjoint operator with respect to the duality, which is based on the intersection product. So you can construct a new pairing between Sue's forms in which you introduce as a correcting factor the exponential of I omega x. This is again a self-adjoint operator. And what you find in this case is that the corresponding Hodge Laplacian, instead of being 0, is given by, essentially, it's the d bar d of omega x. It's the d bar d of the fundamental form. This already indicates that, basically in all applications that I gave of this, it will be based on finding a way of lifting the obstruction which is expressed by the non-vanishing of the d bar d. Actually, bad manifolds are not the ones which are not Kähler. They are the ones with Kähler, the d bar d of the Kähler form does not vanish. Okay, so some thoughts on complex Hodge theory. In classical Hodge theory, the Laplacian is elliptic. In Chern-Weil theory, the Laplacian is nilpotent. We will again develop an interpolation theory via the hypoelliptic Laplacians. We'll find a way of interpolating between these two theories. So first of all, an enlarged space. So exactly like in the real context, I now introduce the total space of the holomorphic tangent bundle. Total space of the holomorphic tangent bundle, and to distinguish the fiber from the base, I call the vertical fiber Tx hat. Tx hat is just a copy of Tx. So let me call y hat. Y hat is the canonical section of Tx hat on the total space, the canonical section of Tx hat. And so it induces a canonical section of the tangent bundle on the base. These two fibers are isomorphic. From Tx hat, section y hat, you get a corresponding section of Tx. And so the first step will be to introduce the causal complex associated with this section y. So y is a section which vanishes exactly on the original manifold x. And so you can introduce the causal complex, which is the holomorphic exterior algebra of the base, equipped with the contraction operator by the section. So actually, you get this way a new complex on the total space of the tangent bundle, which actually is a Dolbeault complex of the total space of the tangent bundle. So it should be here x script, not y script, but x script, twisted by lambda t star x, which is the anterior holomorphic exterior algebra, tensored by E. And it's equipped now with a Dolbeault causal operator. That's an operator differential in hypercohomology. And I have the factor 1 over b squared. There is always a factor, the parameter b. But if you want to forget b for the moment. So this is a Dolbeault causal complex. And actually this Dolbeault causal complex is quasi-isomorphic to the original Dolbeault complex. A restriction map gives you quasi-isomorphism. So from a cohomological point of view, we have not changed anything. So let me explain the construction of a new duality on this new Dolbeault complex. So this duality will be constructed as follows. We give ourselves omega x, which is a 1-1 form, which for the moment does not need to be positive. It could be even 0. Omega x is a 1-1 form of the base. GE is a Hermitian metric on the vector bundle, and GTX hat is a metric on the fiber. You have these three sort of metrics, one on the tangent bundle to the base, one on E, and one on the fiber. And so we will define a Hermitian duality on this enlarged Dolbeault complex on the total space X strip, which essentially coincides in the vertical direction with Hermitian duality, because the vertical direction is equipped with Hermitian metric. And on horizontal direction, it is actually this bizarre duality which produced Turnweil. So we're going to mix classical analysis in the fibers with degenerate analysis on the base. Okay, so this is an essential aspect of the hypoelliptic theory that in some sense it passes all the difficulties coming from Hermitian geometry on the base to something which reflects the Hermitian geometry of the fiber. And by doing this, you get rid of all the difficulties, of all the things which that you could not handle on the base manifold. So, actually, this duality coincides on vertical forms with Hermitian duality along the fiber and with the alpha omega x duality based on the intersection product. Okay, so you combine the two. I will not explain, of course, the detail. So, once you have the operator which defines the hypercohomology, you can take its adjoint, again, with respect to this mixture. You compute the adjoint, and you compute the corresponding Hodge-Laplacian. That's the Hodge-Laplacian with respect to this bizarre duality. So actually, as you can expect, this new Laplacian is still a hypoelliptic Laplacian. So it does have exactly the structure I mentioned as before. It is the sum of two terms up to operators of order 0. In the fiber, you have a harmonic oscillator. You do have the generator of the geodesic flow plus extra terms. And among these extra terms, I will single out again the d bar x, d bar d of omega x. So this d bar x dx of omega x also appears, actually, when you compute the Hodge-Laplacian for Hermitian metric, whose fundamental form is omega x. The d bar x dx of omega x, in that context, is a pain in the neck. So why is it in the pain in the neck? Because for me, when you try to prove Riemann-Roch using the analytic methods, what you find is that actually if the Kähler form is not d bar d closed, you cannot prove Riemann-Roch directly by the so-called analytic methods that we know, which are called the which is the heat equation method. So this d bar x dx omega x still appears here. So why do we introduce this complex hypoelliptic Laplacian? So first of all, as I mentioned before, the point of the hypoelliptic Laplacian is that it transfers metric question on the base to a potential function on the fiber. Right, so you have this y square, which is computed using the metric on the base. But in some sense, while before in the classical Hodge theory, what you had was a second order operator acting on the base, what now it has become is a function along the fiber. So in certain geometric questions, the bad term is precisely this d bar x dx omega x in the elliptic and in the hypoelliptic theory. So in other words, for the moment, for these sort of questions that I wanted to look at, moving from the elliptic theory to the hypoelliptic theory hasn't done any significant progress. The obstacle is still the same. We still have moved to a new theory, but it's still not enough. So let me try to explain now why we have more flexibility with this new theory. I told you that the duality between forms was obtained via the exponential of the two forms in the exterior algebra. But actually, nothing prevents you from taking omega to be zero. Actually, you're in a context now where you allowed it to take extremely degenerate Kähler forms, which is completely forbidden in the elliptic world. And in this case, what we shall do is actually replace omega by scaling the Kähler form omega of the base by y squared. We're going to start making the metric on the base and the fiber interact with each other. So, actually, let me just explain this. I already said that in the elliptic theory, as in this non-modified hypoelliptic theory, the obstacle was a d bar x dx omega x, which appears in Kodaira-Nakano's formula. And so actually, in this new hypoelliptic theory, we now are going to go quite far in the direction of taking degenerate Kähler metrics. We're going to scale omega x by y squared omega x. We're going to take a Kähler metric on the base, which actually depends on the coordinate in the fiber. This obviously was absolutely impossible in the classical Hodge theory. We did not see the point in the fiber. So if we do that, it turns out that the analytic obstacle I was mentioning before is lifted. So actually, by using this technique, we could, in joint work with Shen and Wei, we could prove an extension of Riemann-Roch-Grothendieck to arbitrary, for coherent sheaves, to arbitrary complex, compact manifolds, complex manifolds, which are not Kähler, not projective, nothing. So Riemann-Roch-Grothendieck is true in that category, and a key instrument is precisely the fact that we can move away from classical Hodge theory in the hypoelliptic world. Okay, so here are a few references, and we'll stop here. Thank you very much.
Yeah. Okay, so questions?
In the case where the manifold, base manifold is non-compact? Yeah, I mean, you know, first of all, we are already non-compact in the fiber direction. Now, what you're asking for the base to be non-compact. Yes, I mean, you know, you certainly can do that, but you have extra difficulties which are related to what happens at infinity. The difficulties there are essentially not so different from what the ones you meet with the classical Laplacian. Actually, in the context of my next talk, which will be related to the application of these methods to the symmetric spaces, the symmetric space is non-compact. We will look at symmetric space of non-compact type and we'll work on the symmetric space. So you will see how we can handle this. So non-compact obviously introduces new difficulties, but this can also be handled properly. Yes. So the answer is, if there is a reasonable answer to your question, yes, you can do it. Okay, it's slightly circular.
I have another question about omega. It is also singular in the sense of
Okay, so, I mean, of course, for the theory to work, it's still essential that omega x be non-degenerate on the base, right? But what I'm saying is that if you view it and lift it, you're now able to correct this form by weights, which depends on the coordinates y. Now, you're asking probably more. Can I use singular omega x themselves? Yes. I mean, I would say yes and no. I mean, you know, you're not going to, well, my personal perspective on this is that eventually certain questions which are analytically difficult on the base become easier. Okay, I gave an example which are related to sort of local extractions from differential geometry. Now, what you're asking is if the case where omega x itself degenerates on the base or becomes singular, is it easier to deal with this? So, I mean, this again requires qualified answers, because essentially what you have is, in some sense, a harmonic oscillator where the potential now, the y square, is calculated using the form omega x. If omega x vanishes, say, in certain directions, then y square may tend to become non-zero, may become it doesn't tend to zero at infinity. It will have directions of degeneracy. In that case, the operator is no longer, it doesn't have discrete spectrum. It starts acquiring continuous spectrum. So you have to be very careful here. Maybe you can do that, but certainly, you know, you're not going to, I mean, in other words, this box works to a certain extent. It eliminates certain kind of difficulties. It's not going to make that something which is very degenerate here will become suddenly very easy. It requires more work, but this is for you to do.
Yep.
So, are there generalizations of these things to mildly nonlinear objects, like adding some lower order nonlinear?
Yes, so, I mean, the application in the nonlinear context, again, in the context of symmetric spaces, actually, what you will do is ultimately deal with nonlinear hypoelliptic theory. Okay, so there will be nonlinearities, but this will be a bit complicated to explain. I mean, the question is to know how to construct naturally, right? I mean, in a natural way. What I explained here is that the construction sort of naturally by first principles. When you have a nonlinear equation, you need to understand how by first principles shall I create a hypoelliptic deformation. So this, if you know what equation you have, you probably have the idea of what the deformation should be or should look like. I cannot say a priori, once I have a nonlinear equation, how can I suitably, I mean, nonlinear but still elliptic equation, how can I suitably deform it to a nonlinear hypoelliptic equation? But you know, first of all, you work the linear theory, you linearize, you see what happens on the linear theory and try to extend this in the global setting. But this is again work for you.
Okay, so, yeah, please.
Is there any relation to the form of the closed space?
Is there a connection with superconnections, you would say? Yes. I mean, yeah, because in the context of this proof of Riemann-Roch-Grothendieck for coherent sheaves, actually, I mean, what we used essentially as an essential tool was the idea of the superconnections of Bloch, which are, I mean, in some sense, so Jonathan Bloch explained that there is a category of objects similar to holomorphic vector bundles with connection, through which you can actually represent all the coherent sheaves. So, from this, then we constructed the corresponding classical Hodge theory, deformed it to the hypoelliptic Hodge theory, and finally proved the Riemann-Roch-Grothendieck theorem. So, this is a context in which we put it to work. We combine the techniques of the hypoelliptic theory with superconnections. We combine the two, in some sense, to make at work the two together. Right? They are not conflicting theory. They are tailor-made to sort of fit with each other. Right? I mean, there is a part of the construction I gave is completely algebraic. So once you understand the proper algebra, you see, I mean, you don't have much choice. The point is to have the right starting point. Once you understand the starting point, then everything follows up by analytic continuation. Right, you have no choice.
Okay, other questions, remarks? So then, yeah, let's thank the speaker again. Thank you very much.